Hello, this is Shubh. I'm going to explain you the end semester paper of data science using Python. Starting with question number one, distinguish between hypothesis-driven and data-driven paradigms in data science, and provide an example for each. Definition: data-driven, hypothesis-driven. Start with a theory or hypothesis about the world, and then collect data and run tests to confirm or refute the hypothesis. This is hypothesis-driven. Data-driven. Start from the available data, explore it to find pattern, generate hypothesis, build a predictive model without a strong prior theory. That's data-driven, the paradigms. Our goal in hypothesis-driven is to test casualties or specific scientific claims. In data-driven, our goal is to discover pattern, build accurate prediction, or to generate new hypotheses. The method we use in hypothesis-driven is experiments, controlled trials, A/B testing, statistical hypothesis testing, p-values, or confidence intervals. In data-driven, we use ex exploratory data analysis (EDA), feature engineering, machine learning, unsupervised learning, model selection, etc. We use hypothesis-driven when we have prior domain knowledge or a theory to validate. And we use data-driven when the large data sets exist, but theory is incomplete. Example, user behavior on website. Example of hypothesis-driven is drug X reduced blood pressure more than placebo. Design randomized clinical trial and run a statistical test. Example of data-driven is use click steam logs to cluster users and discover unexpected customer segments, then building recommender system. Now this second part of question first. Differentiate between structured, unstructured, quantitative, categorical data with suitable real-world examples. Structured data. Definition. Organized in table fields with fixed schema, like rows and column. Example, relational database, customer table, customer ID, name, age, balance, CSV skills records. Characteristics include easy to query, numeric, or fixed format string. In unstructured data, definition is the no predefined schema, text, images, audio, video. Example include customer support emails, product images, call recordings. These are all example of unstructured data. Characteristics include requires NLP or computer vision to extract features. Next, quantitative data or numerical data. Definition, numerical values that represent counts or measurements. Types include continuous like temperature, weight, or discrete like number of purchases. Example include house prices, salary, age. Next, categorical data. Definition is discrete label or categories, often non-numeric. Types include nominal, no order, example color, ordinal, with order, like example education level. Example include payment method, cash or card, and customer satisfaction, low, medium, high. Question second, first part, write an algorithm that uses bias theorem for decision making. So we start with the step one. Start. Step two, identify a set of problem possible classes or event C1, C2 till Cn for decision making. Step three, collect prior probability for each classes P, C1, P, C2 till Pcn. Fourth step, collect likelihood values for of evidence E for each classes. PE, C1, PE, C2, PE till Cn. Step 5, compute marginal probability of evidence. Compute marginal probability of evidence. That will be P of E will be equal to summation of PE to Ci into PCi for all classes I. Step 6, the next step, for each class, compute pro posterior probability using Bayes theorem. That's P of Ci by E equals to P of E by Ci multiply P of Ci is to P of E. Step 7, compare all the posterior probability P of Ci by E. Step 8, select the classes with the highest posterior probability as the decision outcome. Step 9, display the selected classes. Step 10, stop. That's the algorithm that we use that uses Bayes theorem for decision making. Part 2 of question number second, write an algorithm, suitable algorithm for association rule mining that can print all the association rules. Step 1, start. Step 2, input the transactional database. Step 3, set the minimum support and minimum confidence threshold. Step 4, generate all the frequent item set from the database using the a priori property. If an item set is frequent, all of its subsets are also frequent. Step 5. For each frequent item set, generate all possible non-empty subset. Step 6. For each subset S of frequent item set F. First, calculate the confidence that will be support F by support S. And if, second part, if the confidence is greater than minimum confidence, then form the rule S implies F minus S. Step 7 is store and print all the association rule that satisfy the confidence threshold. Step 8 stop. That's the rule. That's the suitable algorithm for association rule that can print all the association rules. Thank you. Starting with question number third, first part, compute mean, median, mode, and standard deviation for a given data set and explain when each measure is appropriate. Example of a data set, we take a data set of 2, 4, 4, 6, 10. We calculate the mean by summing all the values in the data set and then dividing by the number of values, that is 5. We get the mean equals to 5.2. The mean is used when the data are interval or ratio scale and not heavily skewed and uses all value. Median, that's the middle value. Sorted data, we have 2, 4, 4, 6, 10. The median value, the middle value will be 4. This is used when the distribution is skewed or contain outliers. Robust. Mode, most frequent value. 4 come twice in the data set, so the mode is 4, and the mode is used for categorical data or to identify the most common or typically value. Multimodal values are possible. Standard deviation. The population SD formula of D is the square of n by 1 by n and summation of xi minus x whole square. Standard deviation gives us the first will be 10.24, next will be 1.144, next will be 1.14, next will be 0.64, and next will be 23.04. The sum of squares of all will be 36.8, and this gives us the population variance of 7.36, and the standard deviation will give us the root by finding the root of it, square root of it gives us 2.713. So the 2.713 is the standard deviation of this, and this is used, SD is used to measure the spread when the mean is meaningful and sensitive to the outliers. Second part of question number B, what is the difference between error and artifacts in data cleaning? Explain any two imputation techniques. Error versus artifacts. Error are incorrect values due to input mistake, sensor fault, transmission error, or human entity. Example, we put 2000 instead of 20. They are invalid and corrupted values. Whereas artifacts are systematic distortion introduced by measurement process or pre-processing. Example, duplicated rows due to logging, rounding biases, sensor calibration biases. Artifacts may be consistent but not true value. Two imputation techniques are mean median imputation. Replace missing numerical values with column mean or median if skewed. Pros, simple, fast, preserve the dataset sizes. Con, underestimate variance, may bias correlations. Use when missingness is small and data fairly symmetric or mean or skewed, then we use median. Next imputation technique is k nearest neighbor, KNN imputation. For each missing value, find the k nearest record using other features. Impute using mean or majority of the neighbor values. Pros include uses multivariate relationship and can preserve structure. Con include computationally expensive and sensitive to scaling or choice of k. Thank you. Question number 4, the first part, explain any 4 common feature engineering techniques for continuous or categorical data. First, scaling and normalization or normalization. Standardization Z score, Z is equals to x minus mean upon by standard deviation. Useful for algorithms sensitive to scale, SVM, KNN, gradient descent, etc. Min and max scaling maps values to range from 0 to 1, preserve distribution shape, but is sensitive to the outliers. Second, binding and discretization. Convert continuous value to categorical bins. Example ages 1 to 18, 1935, 36 to 60, and 60 plus. Uh, this is binding or discretization. Can be done by a fixed width bin or quantile bin. Helps capture non-linear pattern and reduce noises. Third, encoding categorical variables. One-hot encoding. In one-hot encoding, it creates separate binary columns for each category. Best for nominal variable. Ordinal encoding assigns integer values to order categories. Example, low if 1, medium 2, and high 3. Target slash or mean encoding. Replace category with mean of the target variable used with cross-validation to avoid data leakage. Fourth, feature interactions or polynomial features. Create interaction terms such as x1 into x2 or x1 square or x2 square, etc. Helps model capture hidden non-linear relationship, especially linear model. Fifth, missingness indicator. That's optional thing. Add binary column indicating whether the value is missing, 0, not missing, 1, missing. Useful when the pattern of missing values is informative for prediction. Question 5 is to distinguish between parametric versus non-parametric model and supervised versus unsupervised learning with examples. Parametric model uh, parameter defines as assume a finite set of parameters with a fixed dimensionality, example linear regression with coefficient. Its pros include it's simple, fast, and need less data. Its con includes may be biased if the model mis-specified. Examples would linear regression, logistic regression, naive biases with Gaussian assumption. In the non-parametric model, it defines as no fixed parameter count. Complexity grows with data, flexible. Its pros include can model complex relationship. Its con include it requires more data and it can be slower. Example includes KNN, decision tree, kernel density estimation, Gaussian processes. Next, supervised learning. It defines as learn mapping from input X to target Y using labeled data. Examples include regression, predict prices, classification, spam detection. Key methods are linear or logistic regression, SVM, random forest, and neural networks. Unsupervised learning definition discover structure for unlabeled data. Examples include clustering, K-mean, dimensionality reduction, PCA, and association rules. Use cases include customer segmentation, anomaly detection, and feature learning. The second part of question 5, define accuracy, precision, recall, F1 score, and illustrate their computation using a confusion matrix. First, we define what's a confusion matrix. It's a binary classification. Predicted positive slash negative was actual positive and actual negative. TP is true positive, FP is false positive, FN is false negative, and TN is true negative. So define accuracy as it represents overall fraction of correct predictions can be misleading when the classes are imbalanced. The formula of accuracy is TP plus TN by TP plus TN plus FP plus FN. Next is precision. Out of all the predicted positives, the fraction that is truly positive, that's precision. Highly precision means fewer false alarm. The formula of precision is TP by TP plus TF. Recall. It's sensitive slash true positive rate. Out of all the actual positives, fraction correctly identified is recall. High recall means fewer missed positive cases. Fewer missed positive cases. Formula of recall is TP by TP plus FN. Now F1 score. F1 score is the harmonic mean of precision and recall. So therefore the formula of it becomes 2 multiplied by precision multiply recall divided by precision plus recall. And this is useful when the data set is imbalanced and a balance between precision and recall is needed. Example, we have a TP70, FP10, FN20, TN90, and the total will be 1000. Okay, so the accuracy will be 0.97, the precision will be 0.875, recall will be 0.77, and F1 score will be 0.8235. We start with question number 6, part 1. Describe how the coefficient in linear regression are estimated using either the closed form equation or gradient descent. So, the linear model, y equals x beta plus e, where the x is the design matrix, beta is the coefficient matrix. In ordinary least square OLS, we minimize this L beta, L of beta equals mod of y minus x beta whole square. And the closed form equation or the normal equation is beta equals transpose of that design matrix multiplied by design matrix and inverse of this whole, multiplication by transpose of design matrix into multiply y, assuming that design matrix is invertible. Pros of OLS include it gives us exact solution, fast for slow and medium data set, and cons include it is computationally and memory expensive for a very high dimensional data and numerically unstable when the features are multicollinear. Gradient descent. Now, the gradient descent is an iterative method to minimize j of beta equals 1 by 2 n summation of yi minus xit beta whole square. With the update rule, beta implies beta minus alpha for all j of beta, where the gradient delta for all j beta is minus this formula. And variant include batch GD, full dataset, skewetic GD, one sample per update, and a mini batch GD, a small subset. Pros of this include scalable for large data, support streaming data and regularization. Now, cons include it requires learning rate tuning and convergence. Monitoring solution is approximate, not exact. Next, regularization. Ridge L2 modifies OLS solution to beta as a transpose of design matrix into transpose design matrix plus lambda into I. That's identity matrix. And this whole inverse multiplied by transpose of design matrix multiplied by Y. The lasso L1 encourages but has no closed form solution and is solved using convex optimization. Practical note features improved gradient descent convergence and residual assumption like linearity, homoconsistency, and independence should be checked in practice. The second part of question 6 includes second part of question 6 says explain the logistic regression use the logistic function to calculate the probability of a class for a given input example. So logistic regression model the probability of the binary outcome where y is a subset of y belongs from 1 or 2. 1, no, sorry, 0 or 1. It's a binary outcome. It uses linear combination followed by a sigmoid activation. We use sigmoid function here. Sigmoid function does it creates the value of any outcome between 0 to 1. The probability of the positive class is computed using P of y equals 1 by x equals standard deviation of z equals 1 by 1 e to the power minus z, and this is the sigmoid function formula. The output of the model is always between 0 to 1 and represent the probability. The decision threshold, commonly 0.5, is used to convert the predicted probability into a class label. The model is trained using log laws, that means cross entropy, which means minus square bracket log square bracket y log of p plus 1 by 1 minus y log of p log of 1 minus p. The parameters are optimized by maximizing likelihood or minimizing negative log likelihood using gradient descent or Newton's method. Examples include for w point, point 0.5 comma minus 1 and b equals zero point 0.2 and x equals 2 comma 3, z equals minus 1.8, and p is a standard deviation of minus 1.8. This will be equal to 0.1419. So the prediction is class 0 when the threshold zero point 0.5. Logistic regression can be extended to multi-class classification using softmax multi-level logistic regression or one versus rest. Regularization L1 or L2 is used to prevent overfitting. Question 7, part first. Write k-mean clustering algorithm and discuss how initial centroid influential results. K-mean clustering, we'll explain that. Convergence criteria for that. It stops when the cluster assignment do not change or the change in inertia within cluster's sum of square falls below tolerance. It gives us the output that cluster label for each data output and centroid mean point of each cluster. Impact of initial centroid optimizes the non-convex objective prone to local minima. Different initial centroid means it implies different final cluster and inertia. Poor initialization may cause empty cluster or slow conversion or suboptimal clustering. Remedies include k-mean plus initialization. That's probabilistic seeding, which gives us a faster and a better cluster. Second is multiple runs with the different seeds. This gives us a this allows us to choose solution with lowest inertia. Next is domain knowledge. It allows us to smarter placement of initial centroid. Now the k-mean algorithm, how it works. We initialize the k centroid randomly or with the k-mean, then assign each data point to the nearest centroid cluster assignment. Then we update the centroid as the mean of the point assigned to each cluster. Fourth, check the conversion. Stop if the assignment do not change or the inertia change is less than tolerance. Fourth, repeat the step 1, 2 to 4 until convergence. That's how we do it. Mm. Coming to the part 2 of question number 7. We have to write a k nearest neighbor algorithm using Euclidean distance. K and n, k nearest neighbor. Instant based classifiers, the instant bin classifier, will take the input at training set xi yi, where I goes till n, query point x asterisk, and integer k, usually odd, to avoid ties. We find the distance metrics, Euclidean system most common. Okay. Now algorithm. First, compute the distance from query point x to every training sample xi. Sort all the training sample by increasing distance. Select the top k nearest neighbor. Fourth, prediction. In prediction comes classification and regression. In classification, majority voting of the neighbor's class label. In regression, average or inverse distance weighted average of neighbor's target value. Key points and notes includes feature scaling required, normalization standardization because Euclidean distance is a scale sensitive. Time complexity is uh, O(n)(d) per query, where n is the training point and d is the feature, and can be accelerated using KD tree or ball tree in low dimensional data. Choices of k, small k will lead to high variance and overfitting, large k will lead to high bias and over smoothing. So use cost validation to select optimal k. The KNN is a non-parametric and lazy. No aesthetics training and computation happens at query time. Now question number 8, starting with the first part of it, is to compare decision tree, random forest and boosting, highlighting the strength and weakness of each. Starting with decision tree, its strength include it's interpretable and easy to visualize and handles numeric and categorical feature and little data prep. Weakness include prone to overfitting, high variance. It's unstable as small data changes can change tree and greedy splitting may miss global optimal. Now random forests assemble of tree via bragging. Its strength includes reduces variance, robust, often good out of the box accuracy. Handles high dimensional data, less prone to overfitting. Provides feature importance estimates. Weaknesses, less interpretable, Then single tree, larger memory time for many tree, can be biased for categorical variables with many levels, less interpretable, partial dependence, or SHAP sharp use for explanation. Next we come to boosting. Example, ADA boost, gradient boosting, and XG boost. Strength include builds a strong predictive model by sequentially correcting errors, often state of the art, can handle complex relationship feature interaction. Weakness include more sensitive to hyperparameters, risk of overfitting if not regularized, slower to train sequential, more complex to tune, less interpretable, partial dependence, or sharp use for explanation. Part second of question number 8. Explain the architecture and components of Hadoop, HDFS, Yarn, MapReduce, or describe Spark and its advantage over MapReduce. Apache Spark overview. It's a distributed data processing engine. In-memory computations, it supports batches and streaming, SQL, and machine learning. The main abstraction include RDD, Resilient Distributed Dataset, high-level APIs, data frames, and datasets. Core components include driver, that's application coordinator running main and creating RDDs and data frames. Executor includes workers, processes performing tasks and storing data. Next, cluster manager, example Yarn or Mesos or Spark's standalone manager allocates resources. Next, libraries. It includes Spark SQL, Spark Streaming, MLblib, machine learning, GraphX, graph processing. The advantage over machine map reduce is that it's in-memory computation. Spark keeps the immediate data in memory much faster for the iterative algorithm ML than map reduce, which writes to disk between each job. Rich APIs, data frames and dataset API make complex operation for optimizing easier. The iterative shell support. Unified engine, it supports batch, streaming, SQL, and machine learning in the same framework. It has better performance, and it has low latency and fewer disk input-output operations. Next, optimized execution. Catalyst optimizer for SQL data frame queries and Tungsten for the memory layout optimization. When MapReduce is still useful when the very large sample batch job on the disk, when memory resource is limited. But Spark is generally preferred for modern uses. Coming to the question number 9, first part, it is to obtain the basic logic gate from the neural network. I summarize them in a table with the number of neurons, activation function, and backpropagation in neural network, if any. Logic gates implemented by perceptron, single layer perception, not single input perception with a negative weight or threshold and weight and bias point 1.5 activation step output 1 only if the output both output is 1 or weight 1 bias point negative 0.15 activation step output 1 if any input is 1. NAND and NOR is the invert weighted bias of AND and NOR produce NAND and NOR. XOR NOR not linearly separable, needed multi-layer perceptron at least 2 layer. According to the table we are going to explain you, we have the gate and then multiple minimum neuron, and we can explain the architecture, activation function, and then backpropagation. Starting with the AND, it has one neuron. It's a single perceptron architecture. It has a step threshold or sigmoid activation function, and no training needed if the weight set is manually and can be trained via perceptron rule. Coming next to OR gate, it has one neuron. It's a single perceptron architecture. It follows a step or sigmoid again. It is same as AND in for back propagation. Coming to the next gate, NAND, it has only one neuron. It's a single perceptron architecture. It again follows the step or sigmoid and same as AND propagation. Next come to NOT gate. It has one neuron. It's a single perceptron architecture. It follows step or sigmoid function and it is same as AND in the backpropagation. Next come to XOR gate. It has more than or equal to two neurons, hidden layer, two layer of MLP, two hidden plus output. It follows sigmoid activation function or RLU ReLU activation function. Requires training using backpropagation to lead. Now we define backpropagation. It is used to train multi-layer network like XOR, compute gradient of loss with respect to weight via chain rule, update weight with gradient discrete descent, and for each perceptron with step activation, classical perceptron learning rule used instead. Differentiable activation sigmoid enable backpropagation. Starting with the second part of the question 9, compare CNNS, RNNS, GANS, and transfer learning in terms of the architecture and application. Starting with CNNS, convolutional neural network. Its architecture has convolutional layer that filters, pooling layer, fully collected layer, spatial weight sharing, and local connectivity. Application includes image classification, object detection, segmentation, and video analysis. Strength of CNN include efficient spatial feature extraction and translation invariance. RNNs, recurrent neural network. The architecture of RNN and RNN has sequential model with recurrent connections, hidden states, vanilla RNN, STM, and GRU. Applications include sequential data, language modeling, speech recognition, time series forecasting. Strength includes model temporal dependencies. LSTM or GRU handles long-term dependency. Limitations include training issues like vanishing or exploding gradient in vanilla RNN and slower due to the sequential operations. Next we come to GANS, Generative Adversarial Network. Its architecture includes two networks, generator creates samples and discriminator distinguishes from real from fake, trained adversary. Applications include image synthesis, style transfer, super resolution, and data augmentation. Strengths includes produce high quality realistic samples, challenges, training instability, mode collapse, hyperparameter, and sensitivity. Next, we come to transfer learning. It has the idea to reuse the pre-trained model, often from the large dataset like ImageNet, and fine-tune on newly targeted tasks. Application includes fine-tuning CNN for customer burst and transformers for NLP tasks. Strength includes reduce the required data and training and generalization and great for a small data set. It is used when the data is limited and weights exist.